Welcome to RTD Exam Prep Physics 30 Online. In your RTD Physics 30 package, you should have two handouts. You should have your Physics 30 summary notes and your extra practice questions. The summary notes are going to be going over together in all these PowerPoints, and the extra practice questions are just that, for extra practice, for you guys to work on individually and come back in the class and we can talk about it in the Q&A. So let's get started. This first presentation, we're going to go through the beginning of momentum and impulse. This is part 1, momentum to conservation of momentum in one dimension. Impulse and change in momentum. Here we have momentum. Of course, very familiar formula, P equals mv. M is the mass of the object. SI units would be kilogram meters per second. And of course, we remember is a vector quantity, so direction absolutely must be taken into account. The impulse momentum equation. The impulse, which is defined as an object's change in momentum, can be calculated in two ways. We can calculate it using F delta t or M delta v. Units are Newton seconds or kilogram meters per second. Impulse again is a vector quantity, so always remember, take direction into account, especially in, well, not especially in one dimensions, but not too many places where you can kind of mess up multiplying masses and velocities together. But sometimes the place where we do sometimes forget is to keep track of positives and negatives in opposite directions. Cushioning. Why do you bend your knees when you land from a height? And why do cars have airbags? Many applications like this, like airbags, like it says, bungee cords, trampolines, all this same, basically the same kind of stuff. In all cases of cushioning, you're trying to decrease the force on the object. So we start off with our formula for impulse, Ft equals m delta v. You solve for force, and we have m delta v over delta t. And we can see that from that formula, we've got force in the numerator on the left, denominator on the right, we've got change in time, and you see that it's got an inverse relationship. A cushion, what it does, it increases the time to change the momentum. In doing so, this decreases the force on the object. Impulse is not affected by cushioning. That's really important. It's one of the things that we try and sort of distract students with wrong answers for the multiple choice questions. We sort of test whether you know that impulse stays constant if the force changes. So for example, consider a 70 kilogram person who is in a car moving at 30 meters per second. If she comes to rest, the change in her momentum, in other words impulse, is calculated as, so m delta v. Delta v is final velocity minus initial velocity. You work that out, you get negative 2100 kilogram meters per second. So regardless, notice in that formula there, there's no mention of time or force or anything like that. That is the impulse. That is the change in momentum. So this is true if she has an airbag or not. So airbags do not affect the impulse. So let's go over an example here. A 16.0 kilogram object hits the ground with a downward velocity of 62.64 kilometers per hour. If it experiences an impulse from the ground of 500 Newton seconds upwards, determine its final momentum. So let's see, we've got our initial velocity in kilometers per hour, and we've got Newton seconds here, so we need to convert the kilometers per hour to SI units first. So initial velocity, 62.64 kilometers per hour down, as indicated by the negative sign, and then when we convert it to meters per second by conversion factor divided by 3.6, you get the initial velocity to be negative 17.4 meters per second. So we want to calculate the final momentum. Well, let's calculate the initial momentum first. Mass times initial velocity, mass 16.0 kilograms times 17.4 meters per second down. And we get the initial momentum, negative 278.4 kilogram meters per second. Change in momentum is final momentum minus initial momentum. To find the final momentum, it's the initial momentum plus the change. Initial momentum, 278.4 kilogram meters per second down. The change in momentum is 500 newton seconds up. So we got to put positive 500, and we can write kilogram meters per second because it's interchangeable with newton seconds. So you get positive 222 kilogram meters per second, which would be obviously 222 kilogram meters per second up. So at this time I'd like you to pause the video. Is that next? Yeah, pause the video and work on questions 1 and 2 on page 4 of your handout. And when you're done, just hit play again. We'll come back and go over the questions. Question 1. A ball is thrown at 15 meters per second toward various barriers. In which case does the ball experience the greatest impulse? A, the ball hits a wall and rebounds at 2 meters per second. The ball hits a wall and rebounds at 7 meters per second. The ball hits a wall, sticks to it, and stops moving. The ball breaks a window and continues moving at 10 meters per second in the original direction. Okay. So we're not given information about force and time, so we're going to use the m delta v thing. So m delta v, the bigger the change in the velocity, the bigger the impulse, because the mass doesn't change. So we're just looking at the biggest change in velocity for this one. So for A, the initial velocity of the ball was 10 meters per second, and it rebounded at 2 meters per second. So that change in velocity would be smaller than the one if you're going from positive 10 meters per second to negative 17 meters per second, because 10 minus, or sorry, negative, so the change in velocity, right? I'll just do it real quick here. Is final velocity minus initial velocity. So for this one, negative 2 is the final, the initial is 10, so the change in velocity for A would be 8 meters per second. No, it's not, I subtracted it. God, how did I mess this up? Anyway, negative 2 minus positive 10 is negative 12. Man. So for this one, we've got positive 10, get it right this time, off to a great start, and negative 7. So that change in velocity would be negative 17 meters per second for delta V. Whereas for C, the change in velocity would be 10 meters per second to rest. So that would be a change in velocity of negative 10 meters per second. And then, there's obviously a typo here. Let's make this 15 meters per second. I just realized that the booklet does not match what this says. But anyway, the principle stays the same. The change in velocity here would be negative 5 meters per second. So the biggest change in velocity would indicate the greatest impulse. So that would be, well, the answer is B. A rock climber falls and is saved from injuries by a climbing rope that is slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of impulse, because elasticity results in decreased force or increased force, and we've got increased time interval, decreased time interval, etc. So it's that cushioning thing. So remember, force and time have an inverse relationship if the impulse is constant, which it is in this case. So the elastic rope increases the time to change the momentum. This decreases the force on the climber. So that's why the answer for number 2 is A. It's a decreased force during an increased time. Okay, now I'll get back to the notes. We've got graphs here. A force versus time graph. On a net force versus time graph, in order to calculate the impulse, what we do is we calculate the area between the line and the x-axis or t-axis, the one with time on it. So we make note that if we've got positive forces and negative forces, positive force indicated by the green area, negative force indicated by the brown area, we've got positive impulse and negative impulse. Again, momentum and impulse, both vector quantities, you got to keep direction in mind. Okay, I'd like you to take a pause for the video and try question number 3. This graph shows the relationship between the force on a 0.801 kilogram football and the time a kicker's foot is in contact with the ball. As a result of the kick, the football, which is initially at rest, has a final speed of 28.5 meters per second. The magnitude of the maximum force, Fmax, exerted on the ball during the kicking process, expressed in scientific notation, is. So you're trying to find out what this is. Okay, so what we do, the area, remember, is equal to the impulse. So 1/2 base times height. So 1/2 there expressed as 0.5, the base, 0.20 seconds, times the maximum force. So 0.5 times 0.2 is 0.1 times the maximum force. Well, the impulse we can calculate because we were given the mass and the change in velocity. Mass 0.801 kilograms, change in velocity final minus initial is 28.5 meters per second minus 0 meters per second. We set that equal to the expression that we had when we set the impulse equal to the area, and we can then calculate their unknown as the maximum force being 2.3 times 10 to the 2 newtons. And that's the magnitude. Notice the question asks us for the magnitude, so we do not express the direction. Because if we've just asked for the magnitude, they're asking you to ignore the direction. So our answer is A point B times 10 to the C. Values of A, B, and C are 2, 3, 2. Okay, conservation of momentum. Momentum is conserved. In other words, the total momentum in the system remains constant during collisions and explosions. Now, for momentum to be conserved, there's a condition. The system must be isolated. In a non-isolated system, law of conservation of momentum does not apply. The net force on the entire system has to be 0. There can be no outside unbalanced force acting on the system. In other words, all the forces have to cancel each other out. So here we have a collision between two cars. The black car exerts a force to the right on the white car. And based on Newton's third law, the white car exerts an equal but opposite force on the black car. If the forces are equal but opposite, the net force on the system is 0. Thus, the system is isolated. So therefore, conservation of momentum does apply. Law of conservation of momentum. So there's the formula we use. For collisions and explosions, the total momentum remains constant. Quite often we use the little prime symbol right here to represent anything after the collision. Like sometimes you'll see in your book, or your teacher might have used like I for initial and F for final as subscripts. But as you'll see when we get to collisions in 2 dimensions, if you do that, sometimes you're going to have a value with a subscript on a subscript on a subscript with 3 subscripts. Like the x component of momentum A initial equals the x component of momentum A final, whatever, like initial, final, and A. That becomes a little tedious to deal with. It's kind of hard to write. So at risk of offending calculus teachers, because the prime symbol means something else in calculus, we just borrow the prime symbol to indicate anything after, so we don't have to mess around with all those subscripts. So case 1, objects collide and bounce off each other. So you got 2 masses, they're unequal masses, and they're moving towards each other with unequal velocities. So we make sure and use a reference system. So make sure when we're plugging values into an equation, anything to the right here would be positive, and anything to the left would be negative. That's the one thing that we sometimes find students make mistakes on, is forgetting in positives and negatives. Easiest thing to do. Case number 2, we might have a hit and stick collision, like the 2 examples up there. What happens is, for both cases, the objects become one object, essentially, after the collision. So the car and the truck become sort of one moving car-truck combo at the left there. And then on the right, we've got some kind of cart and a brick or something loaded onto it. And notice they move off together as one object. Last case, explosion. Once again, we always start off with the same statement of the law of conservation of momentum in an isolated system. The total initial momentum is equal to total final. At the beginning, everything's at rest. Rifle's at rest, and the bullet's at rest. So the total momentum before the explosion is 0. Well, after the explosion, the total momentum will also have to be 0. So the momentum of the rifle has to be equal and opposite to the momentum of the bullet. So the example problem. Determine the initial velocity of the 800-gram ball. So you got 2 balls going toward each other. One has a mass of 500 grams, the other has a mass of 800 grams. So we'll call this one ball number 1, and we'll call this one ball number 2. We have the initial velocity and the final velocity for ball 1. We have the initial velocity is unknown for ball number 2, but we know its final velocity. So the total initial momentum equals the total final momentum. So the momentum of object 1 plus ball 1 plus the momentum, make that a little bit neater. Momentum of ball 1 plus the momentum of ball 2 before the collision is equal to the momentum of 1 after plus the momentum of 2 after. And we write that out as, masses and velocities. We just plug in the masses to make sure we keep, and when you plug in the velocities, we make sure to keep the positives and negatives straight. So ball A has a mass of 500 grams. It's moving at 30 meters per second to the right, indicated by the positive sign. Ball 2 has a mass of 800 grams. We do not know its initial speed. After the collision, ball 1 changes direction. Now it's going 17 meters per second to the left. So we indicate that with a negative sign. Ball 2 is moving to the right at 9 meters per second, so we indicate that with a positive sign. So the only unknown there is V2. So by the time you plug all those numbers in your calculator and work all that out, you get negative 32.6 meters per second. So the velocity of ball 2 before the collision is 32.6 meters per second to the left. And whether you stick with the negative sign or you just have it as left, doesn't make a difference. As you remember from Physics 20, just don't put both. Okay, so pause the video and please work on the questions 4, 5, and 6 on page 6 of your handout. Make response number 4. A 3,000 kilogram freight car moving at 8.0 meters per second east collides with a 4,000 kilogram freight car moving at 2.5 meters per second west. The final speed of the two freight cars together is blank meters per second. Okay, so there's a little diagram of our situation, and we put in a law of conservation of momentum. This time it's a hit and stick collision. So the total initial momentum equals the total final momentum. We're given everything in the initial situation. The only thing we don't know is the velocity of both of them combined after. So we plug in the masses and the velocities, keeping in mind that the 8 meters per second is positive, and the 2.5 meters per second is negative because positive direction is east, negative direction is west, and the sum of the two masses added together is 3,000 plus 4,000 is obviously 7,000 kilograms. So divide all that out and you get positive 2.0 meters per second. So that means then that they're going to be moving to the right or east at 2.0 meters per second. Questions 5 and 6. Two laboratory carts are placed on a frictionless surface. A spring is attached to both carts and compressed. A string holds the two carts together so that they are motionless. Cart 1 has a mass of m, and cart 2 has a mass of 2.5 m. The string is cut and the carts move in opposite directions. Cart 1 has a velocity of 0.80 meters per second left. Number 5. The speed of cart 2 after the string is cut is. Okay, so conservation of momentum. And total initial momentum is equal to the total final momentum. The total initial momentum is 0 because everything is at rest. So that means the total final momentum has to be 0. So the two carts have to cancel each other out. So we plug in the masses and velocities. Notice the mass of 1 is given as m, and the mass of 2 is given as 2.5 m. So when you solve for the velocity of cart 2, you notice that the m's cancel. So we get an answer of 0.32 meters per second. And that means the answer is D. The spring exerts equal but opposite forces on the carts for the same time, delta t. Thus the impulses are equal but opposite. Since the forces are equal but opposite, the net force on the system is 0. That is, the system is isolated. So which of the following is true about the explosion of the two carts? Impulses are equal but opposite, and the net force on the entire system is 0 because it's isolated. Moving on. Elastic and inelastic collisions. Elastic collisions. To be elastic, the total kinetic energy is conserved. No energy is lost due to heat and sound. Note, for an elastic collision, momentum must also be conserved. So we have to have an isolated system. If kinetic energy is also conserved, then we've definitely got an elastic collision. For an inelastic collision, energy is lost due to heat and sound being produced, so the kinetic energy is converted and not conserved. However, momentum is still conserved. As long as the system is isolated. In this collision, it is. So pause the video and please go through number 7. A 4.0 kilogram toy car moving east at 3.0 meters per second collides with an 8.0 kilogram toy truck that is initially at rest. After the collision, the car is moving west at 1.0 meters per second, while the truck is moving east at 2.0 meters per second. Which of the following is true? Okay, so what we do is we can do a conservation of momentum calculation. The initial momentum is only contributed by the car. It's got a 4 kilogram car moving at 3 meters per second to the right, and the truck isn't moving, so that means the total momentum is 12. After we've got the car and the truck moving, we multiply their masses and velocities together, keeping that the car is now moving to the left, so it's got a negative velocity, and the truck is moving to the right, so it's got a positive velocity. Work that out, and you get the same answer. You get positive 12 kilogram meters per second. So the total momentum is conserved. As far as it being elastic or inelastic, what we do is we work out the total initial kinetic energy in the system is 18 joules, and we find the total energy after to be the same. So in this case, with these numbers here, the total kinetic energy is conserved, so that means you've got an elastic collision. So that's why the answer for number 7 is D. Momentum is conserved and the collision is elastic.